Hey there, and welcome back. Today, we are tackling one of the most incredible topics in all of science, nuclear chemistry. We're going to do a high-level review, which means we're going past the electrons we usually talk about and diving right into the heart of the atom, the nucleus itself.
Pretty much all the chemistry you've studied so far has been about electrons, right? How they move, how they're shared, how they create bonds. But today is different. We're going deeper. We're talking about the immense power and the wild transformations happening right there in the core. It's a whole different ballgame.
So, here's the plan. We'll kick things off with the essential vocabulary. You gotta know the lingo. Then we'll look at the key equations that run the show. After that, we'll tie it all together with a section-by-section summary of the chapter, and we'll wrap up with one big question to get you thinking.
All right, let's officially start this journey into the atom's core. Nuclear chemistry is just fascinating. It really got going back in the late 1800s, and since then, it's completely reshaped our world. I mean, we're talking about everything from the energy that lights up our cities to the medical scans that literally save lives. Okay, before we can really get into the nuts and bolts, we need to speak the language. We're about to do a rapid-fire vocabulary review. I'm not going to read out every single definition. That would take forever. So please feel free to hit pause anytime you want to take a closer look at these terms. They are absolutely crucial. First up, we've got some of the absolute fundamentals. You'll see terms for the basic types of radioactive decay, like alpha decay and beta decay, plus that all-important idea of a chain reaction. Go ahead and pause here if you need a minute. Now, this set of terms is really interesting because it's heavily focused on nuclear reactors and the process of fission. Words like control rod, critical mass, and containment system. These are all about how we manage and harness the incredible power that comes from splitting an atom. This group is a great mix. We've got fusion, which is basically the opposite of fission. We have gamma emission, a super high-energy form of radiation, and we're starting to see some key measurement concepts, like the Geiger counter for detecting radiation and the idea of half-life for tracking how quickly something decays. So the really big ideas on this slide get right to the heart of nuclear energy and stability. Mass defect and nuclear binding energy are totally connected to Einstein's famous equation. They explain where all that incredible energy locked inside a nucleus actually comes from. It's mind-blowing stuff. This next batch gives us the specific language for talking about atomic nuclei, like nuclide and nucleon. We also meet another fundamental particle, the positron, which is the antimatter version of an electron, and we get a look at some of the really important medical applications. What I love about this slide is how it highlights the practical side of all this. You'll see terms for radiocarbon dating, which lets us peek into the past, radioactive tracers used in medicine, and the different units we use to measure the biological effects of radiation. And we'll wrap up our vocablets with one of the most important concepts in the whole chapter, the strong nuclear force. This is it. This is the fundamental force that glues protons and neutrons together inside the nucleus, overcoming that huge electrical repulsion between all those positive protons. Seriously, without it, atoms as we know them just couldn't exist. All right, we've got the vocabulary down. Now let's check out the mathematical tools we use to actually describe and predict what's going on in the nucleus. These are the key equations you'll need to know. And we have to start with the most famous equation in all of physics, E equals mc squared. This is the secret sauce. This is what unlocks the power of the nucleus. It tells us that mass and energy are really just two sides of the same coin. In these nuclear reactions, a tiny, tiny bit of mass disappears, and in its place, a tremendous amount of energy is released. This equation tells us exactly how much. Next up, we have the decay rates. Now, this equation looks simple, but it's super powerful. It basically says that the more radioactive atoms you've got in a sample, the faster that sample is going to decay. That little lambda symbol, lambda, is the decay constant, and it's a unique fingerprint for every single radioisotope. So if you know that decay constant, you can figure out an isotope's half-life. Now, you're going to see this equation written in two different ways, but don't let that throw you. They are exactly the same thing. Whether you use the natural log of 2 or just plug in its value 0.693, you are calculating the exact same number, the time it takes for half of your radioactive stuff to decay.
And finally, how do we measure the actual damage radiation does to living things? Well, that's where these equations come in. They take the raw energy absorbed, which we measure in rads or grays, and multiply it by something called the relative biological effectiveness, or RBE. That's a factor that accounts for how nasty a specific type of radiation is. REM is the older unit, and the Sievert is the modern one you'll see more often today.
Okay, we've got the words, we've got the math, so now let's put it all together. We're going to walk through a summary of the chapter's main ideas, section by section, and see how everything clicks into place. So the first section really gets into that fundamental question of stability. What keeps a nucleus from flying apart? It's that strong nuclear force, and it gets its energy from a tiny bit of missing mass, the mass defect, which is all explained by E equals mc squared. We learn that stability is this delicate balancing act, and that stable atoms live in a narrow band of stability. Oh, and there are even magic numbers of protons or neutrons that make a nucleus extra stable. Next, we learn how to write all this down using nuclear equations. And the big takeaway here is conservation. It's just like in a regular chemical reaction, things have to balance out. In a nuclear reaction, the total mass number, which is the sum of protons and neutrons, and the total electric charge have to be exactly the same on both sides of the arrow. Always. So, why do these unstable nuclei change in the first place? Well, they spontaneously decay to try and reach a more stable, lower energy state. They do this by spitting out particles like alpha or beta particles. And what's amazing is that this process is super predictable. Every radioisotope has its own characteristic half-life that you can measure. And that brings us to the really big energy-releasing reactions. We can actually make new kinds of atoms by smashing particles into existing ones. That's called transmutation. The two most famous types are fission, where a heavy nucleus splits apart, which is what powers nuclear reactors, and fusion, where light nuclei combine, which is what powers the sun. Both of these processes release just unbelievable amounts of energy. But it's not all about giant power plants and stars, right? Radioisotopes have tons of practical uses. They're used as tracers in medical imaging like PET scans, they're used directly in radiation therapy to kill cancer cells, and they even show up in everyday things like smoke detectors. A really important feature for medical uses is that they often have super short half-lives, so they do their job in the body and then they're gone pretty quickly. And finally, the chapter deals with the biological effects of radiation. The truth is, we're all exposed to it constantly from both natural and man-made sources. The most dangerous kind is what's called ionizing radiation, because it has enough energy to literally knock electrons off of molecules and break chemical bonds in our DNA. We also learn that different types of radiation have different levels of penetrating power, with gamma rays being the hardest to stop. And that brings our review to a close. As we've seen, nuclear science is really a story about immense power. The power that holds the universe together, the power that fuels stars, and a power that can be used for incredible healing or for unbelievable destruction. So the question I want to leave you with is this. As we look to the future, what is its most important role for the next generation? Thanks for joining me.